So continuing with section 4.3, 5.3 of chapter 5. Um, so radiation sickness, how much of radiation exposure can lead to sickness or in severe cases, death, okay? So the way they measure that is by conducting LD50 um, LD50 studies, and LD50 is defined as the lethal dose to kill one half of the population. All right, that would result in death in one half of a population. All right, so if they are having a test population and they've exposed that test population to a certain amount of radiation, um, then if it does uh, lead to the death in 50% of that population, that level is then described as the LD50 for that particular species. So here you have the LD50 numbers in REMS of different uh, species like dog, humans, rat, bacteria, and insects. And as you can see for humans, the LD50 is 50 rem. Okay. Um, and then insects and bacterium, they are able to withstand higher levels of radiation exposure. As you can see here, insects can withstand almost 100,000 rem of radiation exposure. So a single whole body radiation of 25 rem will lead to a lowering of the white blood cell count. So 1 rem is 1,000 millirem. We've already talked about that. So 25 rem can lead to a lowering of the white blood cell count. Single dose of 100 rem causes radiation sickness like nausea, vomiting, hair fallout, and so on. Single dose of 400 rem can cause death within a month of 50% of the people who are exposed to it. And a single dose of 600 rem is very lethal and can cause death within the month. That a single dose of 50,000 rem is needed to kill bacteria and up to a million rem to inactivate viruses. So smaller life forms are able to withstand higher levels of radiation. So match each property with its unit of measurement. Activity would be becquerel, absorbed dose would be millirad, biological damage would be the millirem, and the SV sievert or sievert. All right, carbon-14 is used to date artifacts, archaeological artifacts like the Dead Sea Scrolls, because of the fact that it disintegrates very slowly. It takes about 5,730 years for its nucleus to start breaking up. All right, and this is referred to as half-life. So half-life is the time it takes a radioisotope to become half its original mass. So you can see here iodine 131 initially it was 20 milligrams. After one half-life, it became 10. All right, so that time that it took to become half of what it was originally, that's referred to as one half-life. So this continues on. All right, by the second half-life it becomes 5, by the third it becomes 2.5. Now iodine 131, it undergoes beta decay, and so it gets converted into xenon 131. All right, so in beta decay, um, the new element is one place to the right of the original element, all right? So that's why it's xenon, all right? And you can see that the amount of xenon that is formed is going on increasing. So initially it was at 10 milligram because half of that iodine became xenon. And then another 5, if you add to that original 10, that's 15, all right? So there's only 5 of the iodine remaining, and then another 2.5 added to the 15, that's 17.5 of the xenon, and then 2.5 of the iodine remaining. Eventually, all of the iodine will be converted into xenon. So what does the graph look like for this decay, for the breakup of this iodine? If you plot the amount in milligrams versus time, you will see a curve like so, all right? That shows an inverse relationship. That means that as time increases, the amount is decreasing, all right? And so it's not a straight line where they're directly related. It's this kind of curve um, that you see, all right? So this is the decay curve, and every 8 days, you're seeing that it becomes half of what it originally was. All right. Some half-lives of radioisotopes. Now, the ones that are used in medicine and nuclear medicine have to have short half-lives, as you can see here. All right. The shorter the half-life, the better. You don't want it staying in the body for too long and causing more unnecessary damage. All right. So you don't want it being in the body for too long because after all, you're doing this as part of diagnosis or treatment. All right. So radioisotopes used in medicine are chosen with very short half-lives so that they don't stay in the body very long and get eliminated quickly, all right? So technetium-99 metastable is the most used medical radioisotope. It has a half-life of just 6 hours. And unlike iodine, which is specific for thyroid-related medical conditions, technetium-99 metastable is non-specific, so it can go to different organs in different places, and therefore many other diseases, etc., or ailments can be diagnosed and treated with technetium-99. All right. Um, Oxygen, fluorine are used in detecting of blood flow, all right, any stoppages of blood flow, and so on, okay. And then, of course, you have strontium uh, and calcium, which is used in detecting diseases of the bones, etc. All right. Now, when you have radioisotopes with large half-lives, like carbon-14 with such a large half-life, that means it takes 5,000 years for it to become half of its original amount. All right. So this is better used, like I said, in carbon dating of materials, especially in archaeological sites, etc. Um, Now, uranium, those are used in the nuclear reactors to harness nuclear energy. All right, so that ends this section 5.3.